Okay, good morning everyone. Uh, I was little bit late. Okay, so chalo write down. Today we can do some questions, important questions for exam point of view from chapter magnetism and matter class 12. Okay, CBSC syllabus. So I will dictate the question and then we can solve. Okay, first we can go through some MCQ. Okay, write down first question. Which of the following has, which have the following has, which of the following has its permeability less than that of free space, less than that of free space. Okay, options are given: copper, second aluminium, C third bit CuCl2 copper chloride, and last nickel. Okay, last option is nickel. So write down one more time. I will repeat. So which of the following has its permeability less than that of free space? First copper, second B aluminium, C copper chloride, and nickel. Okay, so here always the permeability of a free space is always less in the copper. Okay, so copper is the correct answer. Write down, tick mark that. Then write down next one, because in this is copper is a diamagnetic material. Okay, for first question, copper is a diamagnetic material, and always the diamagnetic material, the relative permeability is always less than 0.999. Okay, so that's what here, that means that is less than 1. So that's what here option is copper, and copper is a diamagnetic material here. That's what this is the correct option. Now write down second question. Which of the following cannot be modified? Next question. Which of the following cannot cannot modify cannot modify an external magnetic field as shown in figure. Okay, write down the options: nickel, Ni, then Si, that is silicon. Okay, Si silicon, then NaCl2 sodium chloride, then last option is copper. Okay, last option is here copper. Okay, and this is what the given figure. Okay, so now I will repeat one more time question. Which of the following cannot modify an external magnetic field as shown in figure? First option nickel, silicon, sodium chloride, and copper, and this is what the given figure. If you observe this figure is nothing but what? Your diamagnetic material, no? So if this is a diamagnetic material, then you can check what all are the given option. So here copper is a diamagnetic material, so answer is nothing but what? Diamagnetic, that is a copper, so which we cannot alter these lines. Okay, external magnetic field. So this is the answer. Last option copper is the correct answer. Okay, write down next question. Which of the following has next question, which of the following has relative magnetic permeability relative magnetic permeability between 0 and 1. Between 0 and 1, options are given. First, aluminum Al, then second, alnico, 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 C, water, and last option, that is sodium. Okay, last option is sodium. So always remember in this chapter what are the materials are given, learn the susceptibility, their permeability, okay, and their strength. So there is a comparative study chart is there for diamagnetic, ferromagnetic and paramagnetic substances. If you learn that, then it is very easy, because in that question examples are also there, so it's very easy to learn and solve the questions based on this all three types of material. So these are very simple and easy questions. They are asking if the which one of the following has relative magnetic permeability between 0 to 1. Okay, so relative permeability between 0 to 1. So relative permeability is 0 to 1. 1 is positive. Okay, so that is always observed in the diamagnetic material, because relative permittivity is greater than 0 but less than 1 in diamagnetic material. It's very important. Okay, so option, now once you get the diamagnetic material, you should know what are the diamagnetic material examples, you should know. So here water is the example of diamagnetic material, so tick the option C. Okay, tick mark the option C. Now next question, write down, if the magnetizing field, next question, if the magnetizing field of a ferromagnetic material is increased, its permeability first option decreases, second option increases, third option remains constant, D, first decrease and then increases, I will repeat one more time. If the magnetizing field of an ferromagnetic material is increased, then its permeability A decreases, B increases, C remains constant, D first increases and then decreases. Okay, so check what is the correct option here. Magnetizing field, okay, and permeability, these two things are very important here. Okay, because based on these words only the answer is there. Okay, your answer is hidden in between magnetizing field and permeability. Okay, so here always you know that formula. Okay, what is the formula? We have mu is equal to, okay, the permeability here, magnetizing field and permeability, there is a relation, no, mu is equal to B by H. Okay, H is nothing but what, the field intensity, no, that is external, magnetized external field. Okay, so what will happen, they are saying, if you are increasing the magnetizing field of a ferromagnetic material, if you are increasing, so this is the external magnetic field, if you are increasing this, then mu is what, increases, no? So there is a inverse relation in between mu and H. Okay, so magnetized external field is there is a and permeability and a permittivity, sorry, permeability, both are in inverse proportion. Then here answer is what? First option is no, decreases. Okay, don't take the option first increases and then decreases. That is not the option. Mu and H are in inverse proportion. They are saying this external magnetized field is increases, then mu is what? Decreases. So option A is the correct option over here. Okay. Now write down next question. Write down this formula also. Okay, don't only tick the question answers. Write down next. A uniform magnetic field gets modified. A uniform magnetic field gets modified as shown in figure. As shown in figure. When two specimens A and B are placed in it. When two specimens A and B are placed in it. Okay, and write down next question. Write down sub part. Identify the specimen A and B. Identify the specimen A and B. Second, how is magnetic susceptibility? How is the magnetic susceptibility of a specimen A from that of specimen B? From that of specimen B. So check how the answer will come. Here the diagrams are given. Okay, ferro and diamagnetic materials are given. So I will draw here both the specimens. Okay, so here the field lines are going like this. Okay, that means this is the, they gave us the diagram. Okay, from that you have to identify which material it is. Okay, so which material it is you have to identify, and once you identify, then you can relate. Okay, what are the questions and how the questions are given. This is the specimen A and this is the specimen B. Okay, so they are asking identify the specimen A and B. Okay, so first is very, just now we did know this is the diamagnetic. This is the diamagnetic material, and B is nothing but what here we have a paramagnetic material. Paramagnetic material. So for identification, correct identification, you will get 1 mark. And they are asking susceptibility. Okay, so susceptibility is always in diamagnetic material, susceptibility is always small. Okay, small, but it is positive. Small but positive value. And susceptibility for B is always small. So this is small and negative, and this is small and small positive value. Okay, so this is small negative value and paramagnetic small and positive value. Okay, getting this. Okay, so only you have to write this much, so that answers give you 2 out of 2. Getting this? Very simple answers are there. You should learn the table. If you learn the table which I gave, so it's very easy to answer all 1 mark question. Write down next question. A bar magnet has magnetic dipole moment. A bar magnet has magnetic dipole moment m bar. M bar, its initial position is parallel. Its initial position is parallel to the direction of uniform magnetic field B bar. Uniform magnetic field B bar, full stop. In this position, the magnitudes of torque and force. In this position, the magnitudes of torque and force acting on it respectively are first option 0 and MB. 0 and MB. Second option MB and MB. C 0 and 0. Last option M bar cross B bar and 0. M bar cross B bar and 0. Okay, I will repeat the question. A bar magnet has magnetic dipole moment M bar. Okay, its initial position is parallel to the direction of uniform magnetic field B bar. In this position, the magnitudes of the torque and force on it is respectively are first option 0 and MB, second option MB and MB, third option 0 and 0, and last option is M bar cross B bar is equal to what? 0. Okay, so here the bar magnet is kept in the uniform magnetic field. Okay, and they are saying it is parallel to the magnetic field. Okay, only these two statements are enough to write the answer, enough to choose the correct answer. Suppose this is the magnetic field. Okay, this is what your magnetic field B bar, and suppose if I kept a bar magnet over here, and bar magnet, what they are saying, they are parallel to the magnetic field line. So this direction is also what? Parallel to the B bar. Okay, so if that is parallel to the B bar and they are saying relation of torque, so tau is equal to what? We have MB sine of theta, no? Okay, and if they are parallel, means this magnetic dipole moment is parallel to the direction of the magnetic field, then here theta will become how much? 0. So we can write tau MB sine of 0 is 0 here. So tau we will get 0. If torque is 0, that means force produced over there is also 0, because tau and F both are what? Related quantities. Okay, rotation analog is a tau, no? F is rotation analog of a tau is F. So here we can write tau is also 0 and F is also what? 0. So only from the statement it is parallel to the magnetic field, from that you can write here tau is equal to 0, means angle between them is 0. If angle 0, then you will get tau is also what? 0. Getting this? Okay, copy this. If you want, you can write down that explanation and diagram too, and take the option C here, 0 and 0. Now write down next question. Which of the following statements is correct? Is correct. First, a magnetic field lines do not form a closed loop. A magnetic field lines do not form a closed loop. Second, magnetic field lines start from N, capital N. N means north. N end at S. of the magnet. S means south, ends at south of a magnet. Okay. CBT is given. The tangent at a point on the magnetic field line. The tangent at a point on the magnetic field line represents the direction of magnetic field represents the direction of magnetic field at that point. Magnetic field at that point. Last option, two magnetic field lines may intersect. Two magnetic field lines may intersect with each other. Okay. So here I will repeat the question. Which of the following statements is correct? First, a magnetic field lines do not form a closed loop. Okay. Magnetic field lines start from north and end at south of the magnet. See, the tangent at a magnet on magnetic field lines represents the direction of the magnetic field at that point. And two magnetic field lines may intersect with each other. So they are asking which statement is the correct statement. Okay. So first, magnetic field lines do not form the closed loop. The magnetic field start from north and ends at the south pole. Okay. Now tell which one is the correct. So option here, which one is correct? Actually, the following statement, check which option will come. Here option C is the correct answer. Okay, the tangent at that point on the magnetic field line always represents the direction of magnetic field at that point. Okay, C is the correct option. Okay, so write down one question based on assertion and reason. One, write down assertion. The poles of a bar magnet cannot be separated. The poles of the bar magnet cannot be separated. Reason, magnetic monopoles do not exist. Magnetic monopoles do not exist. Okay. Monopole do not exist. So here assertion is also true, no? Because if you cut the bar magnet, again you are getting two poles, north and south pole. Okay. So if you cut the poles, then as much as possible, always it forms the two poles. Okay. So monopole does not exist. So A and R true, and R is the correct explanation. A and R are true. Okay, so one more question. This is very IMP question, or maybe this question comes for 3 marks. Okay, write down. Two identical circular loops P and Q. Two identical circular loops P and Q, each of radius R. And carrying currents I and 2I. And carrying the currents I and 2I respectively are lying in a parallel planes such that they have common axis, full stop. the direction of current in both the loops, the direction of current in both the loops is clockwise seen from O, seen from O, which is equidistant, which is equidistant from the both loops, from the both loops. Full stop. Find the magnitude of a net magnetic field. Find the magnitude of the net magnetic field at point O. Very IMP question. Two identical circular loops P and Q, each of radius r, small r, carrying a currents I and 2I respectively, are lying in the parallel planes such that they have a common axis. The direction of current in both the loops is clockwise as seen from O, which is equidistant from both the loops. Find the magnitude and net magnetic field at a point O. Okay, so from this given information, try to draw the diagram here. Okay, or sometimes they used to give the figure. Very important question. Okay, it's very easy but very important. So here we have a plane. Okay, we have a plane, and here we have the two circular loops are there. Okay, and this is the midpoint O. There is a P. O is a point. Okay, and the plates are separated by a distance 2r. Okay, plates are separated by a distance 2r because each one is having radius r. Okay, so the total distance between this is nothing but 2r. That is given actually. Okay, this is the P and this is the Q loop. Okay, these two loops are given, and we have the point O. So here, suppose if you are observing from O, you can see the current in this is a clockwise direction. Okay, and if you are observing for here, then the current is also what? In the clockwise direction. Can you getting this what I am saying? So now check, if you observe, then both the directions from O, here is also clockwise, there is also clockwise. In one loop I amount of current is flowing, and another loop 2I amount of current is flowing through this. Okay, can you getting the diagram? What is the diagram is here? Okay, now we have to calculate the total magnitude of the net magnetic field. Okay, we have to calculate the net magnetic field. So here, how can you calculate here? We did one derivation. Okay, so can you able to see the magnetic field due to this P is nothing but BP over here. Okay, and we can take here BQ. So this BQ magnetic field is over here. This is this magnetic field. So can you join here? Okay, see, now can you able to understand which formula we have to apply here? Okay, on the axial point we will at one point P, from that from the center of the loop. Okay, we can drop these lines and we can calculate. So magnetic field at the center. Okay, magnetic field due to circular loop on their center, along their center. So if I write here magnetic field for this, magnetic field for P I will write. So what is the formula? Mu naught I into R square. Mu naught I into R square divided by, we have a 2 into R plus 2 into R square plus R square raised to 3 by 2. Can you getting this? Okay. So suppose another radius is there, or a square. This one radius is this and another is this radius. Okay, that distances are given. So this is what we have a BP here. So if it is pointing towards the P, if you simplify this, so here mu naught I into R square divided by 2, and R square is nothing but 2R square raised to 3 by 2. Okay, so here if you multiply each 3 by 2 inside the bracket, so mu naught I into R square, this 2 and this 2 get cancelled, R raised to 3 we will get, and 2 raised to 3 by 2. we will get that 2 raised to 3 by 2 into 2 is nothing but 4 root 2 into r cube. So here I will erase this r square because anyhow it is get cancelled, only r will remain. So mu naught I upon 4 root 2 into r. This is what the magnetic field at the point P. Now suppose if we are taking this another loop dq. So now how much is the current? Only current value will get changed here, no? Because here formula will remain same, mu naught. Here I amount of current is flowing and here 2I amount of current is flowing into r square upon 2 into r square plus r square raised to 3 by 2. Again you can simplify this. So after simplification you will get here answer is this mu naught upon I upon 4 root 2 into r, okay, which is pointing towards the which is pointing towards the point q bar. Okay, so if you simplify here, 2 into mu naught 2 into I r square, 2 into we have r raised to 2 and here 2 is there, 2 r raised to r square into 3 by 2, 2 and 2 get cancelled, again 4 root 2. So here I will cancel, why I write 2 here, so mu, this 2 is get cancelled, so I r square upon, here I will write 3, 2 raised to 3 by 2 into r cube, okay, r cube means r is get cancelled and you will get it here mu naught I upon again 4 by 4 into r, 4 root 2 into r. So this much is the answer I am getting. Okay, so now check here. Once you get this, then result a net magnetic field at point O is nothing but what? Here both are one is, this is also clockwise and this is also clockwise. Okay, if you add this, then what you will get the answer? You can add both the magnetic fields, then you will get the answer. Okay, magnetic field, no, we can't add because observing from A is a clockwise and observing from B is also clockwise. Both the directions are exactly opposite. Okay, you can subtract it, then you will get the answer. Resultant magnetic field at point O due to P and Q. Getting this? Find out. Okay, finish this. Write down next question. Draw the diagrams. Write down. Draw the diagrams to depict the behavior. Of magnetic lines. To depict the behavior of magnetic field lines near a bar magnet. Of first copper, second aluminum, third mercury, cooled at a very low temperature, 4.2 K. Okay, so here draw the diagrams to depict the behavior of a magnetic field lines near a bar of first copper, second aluminum, third mercury, cooled at very low temperature at 4.2 Kelvin they are saying. So we have to draw here the magnetic field lines, but before that here the some sub questions are there for copper, aluminium and mercury. So you must know what are the examples, which material examples are there. Okay, copper is always comes under diamagnetic material, aluminium is always comes in paramagnetic material, and here if we are taking mercury, then at cooled at low temperature 4.2 Kelvin, then it is always acts as a superconductor. Okay, so it behaves as a perfect diamagnet. Okay, so no lines of force passing through it. It's very important identification of the magnetic material. Okay, without identification you can't draw the diagram. Okay, so learn the examples of diamagnetic, paramagnetic materials. Very important. Okay, so here we can write for first I will make a 3 column. First is for copper, then after that we have the aluminium, okay, and Hg, that is mercury at low temperature. At low temperature, or it is what they are saying, at very low temperature. At very low temperature, that is something 4.2 Kelvin they give. Correct. Copper is, remember, always a diamagnetic material. Diamagnetic material. Then aluminium is always acts as a paramagnetic material. Paramagnetic material. And Hg at very low temperature acts as a superconductor. Okay, it is acts as a superconductor. So it acts as a perfectly diamagnet. So no magnetic field lines are passing through that magnet. Okay, so here diamagnetic. Just now we did 2 questions on the diamagnetic. So draw these figures. Okay. So make the notes accordingly, properly, and you can don't leave this kind of questions. Okay, very easy and marks giving questions. Okay, don't forget to support the arrows. Okay, and for Hg I will draw, this is written here. Okay, so it can make a perfect loop, and then these lines are passing through this. Getting this? Copy this. Okay. So these are the getting this. Okay, copy this. Yes, finished. Write down one more question. A solenoid has core of material. A solenoid has core of material A solenoid has a core of material. Can you able to see the board properly? Okay, write down here. A solenoid has core of material with epsilon r equal to 500. With epsilon r is equal to 500 and its windings carry a current of 1 ampere full stop. The number of turns of the solenoid is 500 per meter. What is the magnetization of material? Nearly magnetization. What is the magnetization of a material nearly? What is the magnetization of material nearly? Okay, I'll repeat this question. A solenoid has a core of material with epsilon r is equal to 500 and its winding carry a current of 1 ampere. The number of turns of the solenoid is 500 per meter. What is the magnetization of material nearly? Okay, this is very IMP question. We can't say whether they will ask this for 1 or 2 marks. Okay, but most of the time students are not learning the formulas from this chapter. Okay, very easy formulas are there, but they are not able to do the formulas for this. If they don't know the formula, then it is quite difficult to solve the numericals. Okay, simple numericals are there. So here one solenoid is given and has a core material with epsilon r. Epsilon r is nothing but what? Relative permeability. Okay, so here relative permeability is given. Just wait. Relative permeability epsilon r is given 500. Correct? No, 500 only. Correct? 500. And then after that they are saying its winding carries a current of 1 ampere. So I is given 1 ampere and number of turns of the solenoid is 500 per meter. Okay, that number of turns is nothing but what? 500 per meter. They are saying, and what is the magnetization of a material nearly? Okay, so we know that M is nothing but we have psi into H. Okay, we have psi into H. Then psi is nothing but susceptibility. Okay, psi is nothing but what? Susceptibility. And see, H, I will write this H as a capital H. And here H we don't know. H also we don't know. Susceptibility also we don't know. But we have to calculate here magnetization, capital M. So here always remember H is nothing but the number of turns into current I. Okay. So number of turns per meter is given 500 and current is given 1. So H value you will get it as 500 ampere per meter. You will get ampere per meter. Okay, so this is what H we will get. Then what about the psi? Psi also we don't know, but psi we can calculate as a epsilon r minus 1. Remember, okay, not epsilon r, mu r. This is magnetic chapter, sorry. So mu r, relative permeability. Yeah, this also should be mu r. Okay, so mu r should be this. Okay, mu r is nothing but what here? Mu r is given 500. Okay, 500 minus 1 is 499 is nothing but what your psi value. Okay, once you get the psi, then substitute both the values no here. So this is 499 into 500. Okay, H is nothing but 500. If you substitute and if you calculate the answer, you will get the answer 2.5 into 10 raised to 4 ampere per meter. 4, no, not 4, plus 5 ampere meter is the answer. That's it. Okay. So this is 1 2 mark question. How we are flipping the formula to get the answer from the given quantities is very important. So people are thinking why I is given, why number of turns are given, because magnetization here is m is nothing but psi into h, but value of psi is not given, h is not given. We have to calculate the value for psi as well as h. Okay, h is nothing but n into I, and psi nothing but mu r minus 1. So related all the values means n, I, mu r, everything is given. So calculate the value for h and psi and substitute in the magnetization formula and you will get the answer. Can you getting up to here? Okay, write down next question. Write down one more question. What is the magnitude of equatorial and what is the magnitude of the equatorial and axis fields due to bar magnet of length 5 mm 5 mm at a distance of 50 centimeter from its midpoint. The magnetic moment of a bar magnet is 0.40 ampere meter square. The magnetic moment of a bar magnet is 0.40 ampere meter square. Okay, I'll repeat this question. What is the magnitude of the equatorial and axis fields due to bar magnet of length L 5 mm at the distance of 50 centimeter from its midpoint? The magnetic moment of the bar magnet is given 0.40 ampere meter square. Okay, ampere meter square. So this is the question. So in short, we have to calculate the bar magnet at the equatorial point and magnetic field at the axis. Okay, so I hope I remember the formulas. You know the formulas. The magnetic field at the equatorial plane and magnetic field at the axis. Formulas are what here? So I will write here the magnetic field at the equatorial point is nothing but what? Mu naught m. Okay, mu naught into capital M, that is dipole moment, upon we have 4 pi r cube. Okay, substitute the value. Mu naught upon 4 pi is nothing but 10 raised to minus 7. Here magnetic dipole moment is given how much? Magnetic dipole moment is nothing but 0.40 ampere meter square. No, 0.40 ampere meter square. R cube, distance r from the, this is how much? They are giving it as a 5, correct? 5 mm. 5 mm means 5 into 10 raised to minus 3 cube. So this will come 10 raised to minus plus 9 into 0.40 divided by, we can write it as 125. Then you can simplify this, you will get the answer something 3.2 into 10 raised to minus 3 Tesla. Okay, this is what the answer you will get. Not Tesla, also I think Gauss 1 by meter, no? So Gauss will come, and B axis is nothing but what? Mu naught upon 2m. Okay, mu naught into 2m divided by, I will write it as 2 pi into r cube. So to adjust this, Then now calculate this answer. Check how much is the answer. Now here I will multiply one more time by 2. So mu naught upon 4 pi. Multiply and divide. So if I multiply here 2 and here also I will multiply by 2. So mu naught upon 4 pi is nothing but 10 raised to minus 7, and this is 4 into 0.40 divided by 5 into 10 raised to minus 3 cube. Okay, simplify this. Once you simplify, then you will get the answer as a 6.4 into 10 raised to minus 3 Gauss. Okay, so simplify, or whatever the answer you are giving, no, coming here the formula you can adjust accordingly. Half of the formula is same only. Okay, just you can multiply and divide and then you will get the answer 6.4 into 10 raised to minus 3 Gauss. Okay, why Gauss comes? Because here the values means Tesla ke liye we are getting meter square above, but here we are getting down, so we are writing this in terms of Gauss. Okay, finished. Write down. A closely wound solenoid of 800 ton. A closely wound solenoid. A closely wound solenoid of 800 tons. And area of cross section 2.5 into 10 raised to minus 4 meter square. 2.5 into 10 raised to minus 4 meter square carries a current of 3.0 ampere. Carries a current of 3.0 ampere. Explain the sense in which the solenoid acts like a bar magnet. Explain in which the solenoid acts as a bar magnet. Solenoid acts as a bar magnet. Full stop. What is its associated magnetic moment? What is its associated magnetic moment? Associated magnetic moment. Okay, so I'll repeat. A closely wound solenoid of 800 tons and area of cross section is 2.5 into 10 raised to minus 4 meter square, carries a current of 3.0 ampere. Explain the sense in which the solenoid acts like a bar magnet. What is its associated magnetic moment? Okay, so here magnetic moment, closely wound solenoid. Okay, solenoid is there and solenoid is having 800 tons. Okay, that means N is given here 800 tons. Okay, and what other things are given? Yeah, number of tons are, N is nothing but we have 800 tons. Okay, we have 800 tons. Then after that we have a area of cross section A is nothing but 2.5 into 10 raised to minus 4 meter square. This is area given, and after that carries a current. I is also, we will, I think how much, 3.0 ampere. So 3.0 ampere, this is the current, and they are asking here magnetic movement associated with it. So magnetic movement is nothing but M is equal to Ni into A. Okay, so number of turns are given 800, I is 3 and this is 2.5 into 10 raised to minus 4. Okay, so do this multiplication and you will get the answer 0.6 ampere meter square. So this unit magnetic movement unit is ampere meter square. Okay, so explain the sense in which the solenoid acts like a bar magnet. What is it? Yeah, and how to explain this? Here, if you take a solenoid, okay, if you take a solenoid, okay, and if you take the smaller area, okay, this is nothing but what, one kind of loop only, no, correct? This is what, one kind of loop, and current is what, entering here and coming out, and again it is entering into the second loop and going into the second next loop. Okay, so this is nothing but what, there is a, it is going from, again what, if you apply here north to south it is going. So if you means what, here uniform magnetic field lines are forming in the solenoid, and if you take a bar magnet north and south pole, there is also what, the field lines are always moving from here north to south, so they resembles the same. Okay, so that is nothing but answer. Okay, write down this, copy this. I hope you all are getting. Copy this. Finished. Everyone copied. So write down next question. The variation of intensity. Next question you can write down. The variation of intensity of magnetization I. The variation of intensity of magnetization I and applied magnetic field intensity H. Applied magnetic field intensity H, capital H, for three magnetic materials, X, Y and Z, are as shown in given graphs. Okay, first bit they are asking, write down first bit, identify the materials X, Y and Z. Identify the materials X, Y and Z. Okay, second bit, show graphically the variation of susceptibility. Show graphically the variation of susceptibility with temperature for X. Third one, put Y and Z, comma, which of the material which of the material will you prefer for making transformer cores, cores, and why? which of the material will you prefer for making transformer cores and why? Okay, so I will repeat this one more time. The variation of intensity of magnetization I and the applied magnetic field intensity H for the three magnetic materials X, Y and Z are shown in the given graphs. Okay, first identify the material X, Y and Z. Second, show graphically the variation of susceptibility with temperature for X. And last one, that is put Y and Z, which of the material will you prefer for making transformer cores and why. Okay, so here the graphs are given. I will draw the graphs and I will give you some time to identify the materials. Okay, so how you can think to find out these magnetic materials. Okay, so this graph based questions are comes most of the times. Okay, so this is what the graph given. This is y axis, this is x axis. Okay, so here they gave a magnetization, here current I. Okay, this is the current I. So here this is x. Okay, sorry, not x, this is y, this is y, this is z, and we have this as x. Okay, so check the graph H versus I. Now find out. Okay, so everything is given. I is nothing but intensity of a magnetization, H is nothing but magnetic field intensity, and first we have to find out the materials. Okay, find out this material, how to identify this material, check. So what are the three materials we have? Paramagnetic, diamagnetic and ferromagnetic materials are there, correct? Check what are the materials you will get. Okay, so here as the H and I is given. Okay, so from this you have to identify the materials. So susceptibility, if you take here the ratio, we know that H by I, that means that indirectly they gave the susceptibility. So susceptibility X or this psi is nothing but we can write as I by H. Okay, so I by H, and here I is nothing but what? Intensity, and H is nothing but what? Magnetic field intensity we have. Okay, so here if we take a paramagnetic material, then paramagnetic are what? Small but positive. Okay, so small but positive, and this paramagnetic I by H is what? Negative when the material is diamagnetic. Very important. The X is nothing but what now? X is nothing but your diamagnetic material. This is nothing but diamagnetic, because diamagnetic material susceptibility is always small, always negative and small. So X is here diamagnetic, and just now I told you I by H, this susceptibility we are getting small but positive, that is nothing but your paramagnetic material. Okay, so that is nothing but what your Z. So this is nothing but what? Paramagnetic material. And this is nothing but what? Remaining is ferromagnetic material, because this intensity means psi is positive and more than one value is always there in the ferromagnetic material. So very important, what is given? H versus I graph is given. That means this ratio gives the susceptibility. You should know that susceptibility for a diamagnetic material is always small but negative. For paramagnetic it is small but positive, and for ferromagnetic susceptibility is always positive and always greater than 1. Okay, then only you can identify. For correct identification you will get, if this question for 3 marks, then they will give 1.5 mark for this, and remaining half they are asking. Second one, show graphically the variation of susceptibility with the temperature. Okay, with for X. For X is nothing but what? Diamagnetic. Okay, so here as it is diamagnetic, negative value, so Xm is small and negative. So if you remain, it is acts as a diamagnetic, it is unaffected due to change in temperature. It will not change, means this diamagnetic materials temperature, if you are changing, it does not affected. You will get what? The constant graph only. There is a no change will takes place. Okay, this is the temperature, and this is what? Susceptibility. Susceptibility of the diamagnetic material will remain same. It will not change. Okay, getting this? So this is what the second bit. Then third bit they are asking, put Y and Z in which of the material will you prefer for making transformer cores and why. So we are preferring here Y material for preparation of the transformer. There we require the require high permeability, okay, and low hysteresis loss we require. So that is the reason we are using ferromagnetic materials in the transformer. So Y material we are using to formation of the transformer, okay, because they have more or larger value of permeability and low hysteresis loss. Okay, so that's what we are choosing Y. Getting this? Okay, I hope you are getting these questions. These all questions are very important for the exam point of view. My request is that you can watch this from the beginning and try to learn the questions again and again. Okay, everyone copied this, wrote the values on the graph. Okay, write down one more question. A uniform magnetic field exists in the space. A uniform magnetic field exists in the space in the plane of paper, in the plane of paper and plane of paper and is initially directed from left to right, left to right, full stop. When a bar of soft iron, when a bar of soft iron when the bar of soft iron is placed in the field parallel to it, is placed into the field parallel to it, parallel to it, parallel to it, the lines of force passing through it, the lines of force passing through it, the lines of force passing through it is represented by, okay, and they gave 4 options. This is option A. Then you can draw the second option. Second option is this. Then option C we have okay, and option D we have okay. So these are the 4 figures are given, okay, options are given. So uniform magnetic field exists in the space in the plane of paper and it is initially directed from left to right, okay, initially directed from left to right. When a bar of soft iron is placed in the field parallel to it, the lines of force passing through it will be represented by. So by reading this, option D is get cancelled because initially magnetic field is going from left to right. Okay, so if you observe the figure, A, B, C all are going from left to right. Okay, option D get cancelled. Okay, we will get only 3 now. Out of 3 we have to choose correct one. So wrong one already gone. Now this is soft iron core and all these things are asking, that means this is related with the ferromagnetic material. So permeability of a soft iron core is maximum. So maximum force of lines tries to pass through the soft iron. Okay, so they are what, as they are going, okay, they are going through this material only, but they are not attracted strongly. But here what, while going they are going straight line, but while going through this they are attracting towards this material. Okay, all the lines are what, more crowded, more concentrated. The field lines are what here, more strength, having more strength. So option B is the correct option, and this we can observe because here as the density is more, that means here relative permeability is also more, and this kind of nature we can observe in the ferromagnetic material. So option B is the correct option over here. Getting this? Now write down next one. The figure below shows the north and south pole. The figure shows below the north and south pole of permanent magnet in which small n turn coils, n small n number of turns, okay, n turns coil of area of cross section A is resting, comma, such that for a current I pass through it, such that the current I is passed through it, current pass through it, The plane of the coil makes an angle. The plane of the coil makes an angle theta. Makes an angle theta. Makes an angle theta with respect to the direction of magnetic field. With respect to the direction of magnetic field. With respect to the direction of magnetic field B, if the plane of the magnetic field B, if the plane of the magnetic field is B. Okay, so they are asking here the torque will be, next line, the torque will be, they are giving option A, tau NIAB cos of theta. So tau is nothing but NIAB sine of theta. Then tau is nothing but NIAB. Then D, none of the above. Okay. So option A, B, C and D are given. So whatever the statements are given here, the north to south pole of the permanent magnet, the turn coil of cross section area is A, and from here the current is passing through this coil, north and south field is, now pole are there, then uniform magnetic field is what formed over here. Okay, so here the option they are asking how much is the torque produced, and we know that torque is nothing but what, NIAB cos of theta. So this is what your correct option. Option A only is the correct option over here. Okay. Write down next the variation. Okay, getting this, copy this much and then write down next question. The variation, next question is very important. The variation of magnetic susceptibility. The variation of magnetic susceptibility with the temperature of ferromagnetic material. With a temperature of ferromagnetic material. With the ferromagnetic material can be plotted as. Okay, so option A is given. So this is temperature, this is susceptibility of the magnetic material, and that is given like this. So B, we have temperature and this is susceptibility of the material, and this is decreases. Okay, and here C, again temperature, and here we have a susceptibility of the material and this is increases, and D option we have like this. Okay, so this is nothing but what, T, and this is X. So it is very important, the susceptibility decreases as increases the temperature. Okay, susceptibility is always in case of ferromagnetic material, okay, decreases with increase in the temperature. Okay, and just now I told you for diamagnetic material that does not affect it, that's what we are getting a constant graph. Now here we have what, we have the ferromagnetic material, they told also the susceptibility of a ferromagnetic material. So susceptibility decreases as the temperature increases. So option B is the correct option over here. Can you getting this? Okay, so tick mark the option. Okay. We are doing last question, after that I will stop. Write down here, the magnetic needle suspended parallel to the magnetic field, the magnetic needle suspended parallel to the magnetic field require requires root 3 joule of work. Root 3 joule of work. Root 3 joule of work to turn it through 60 degree. To turn it through 60 degree. Full stop. A torque needed to maintain. A torque needed to maintain the needle. A torque needed to maintain the needle in this position will be. In this position will be. First option given 2 root 3. 2 root 3 joule. B 3 joule. B 3 joule. C root 3 joule. C root 3 joule. D 3 by 2 joule. 3 by 2 joule. Okay. So here magnetic suspended root 3 joule of work is required to rotate through 60 degrees. Okay. Angle is given. Okay. And we know that work done. Here they are asking they give the option in terms of joule. That means we have one potential energy ka formula, and that potential energy P, or we can write it as work done, and that work done is nothing but what? Minus MB cos of theta minus cos of theta 1. Okay, you can write it as what? Cos of theta 2, and this is 1. So here what are the given things are given? Work done is given, no, root 3 joule. Okay, so this is root 3. This work done or potential is given root 3. After that they are saying minus M into B. M into B, and they gave cos 60 and 0. Yeah, and they are rotating in the magnetic field. So I will keep minus MB, and here I will write cos of 60 minus cos of 0. Okay, so cos 0 is 1. So minus MB cos 60 is nothing but half minus 1 is nothing but, we will get it as a MB. We will get here minus half. Okay, minus and minus will become plus. So this we will get MB by 2, and we can write here MB is nothing but what? 2 root 3. This is what the answer we are getting. So but yeah, they are calculated in terms of joule. Okay, so what they are saying here, MB is how much? Is they gave something? Suspended root 3 joule of work to turn this. Torque needed, tau is equal to MB. MB we are getting root 3 by 2. Yeah, MB is nothing but 2 root 3. So option is here. Yeah, option A is the correct option. Check here, option A is the correct option. Okay, work done we are getting this MB is equal to twice into root 3. But they are asking here the position, the torque needed to maintain the needle in this position will be to maintain this position. Maintain this position means they are asking tau is equal to MB. That 60 we have to maintain here. Okay, for maintaining. They are not only asking MB, they are asking to maintain this. So we can write here tau is equal to MB sine of theta. So MB we can substitute here 2 root 3 into sine theta is sine 60. Okay, sine 60, no, to maintain this sine 60 we require, and sine 60 is nothing but how much? We have root 3 by 2. Okay, so 2 into root 3 into root 3 by 2, 2 get cancelled, and root 3 into root 3 is nothing but what, 3 joule. So this is what the answer. Okay, see, read half the question and I got 2 root 3, but they are asking the needle which we have to maintain, and they are asking torque tau. So that tau is equal to mb sine of theta. So maintain at a 60 degree. So put the value for 60 here, and then you will get the answer root 3 joule, only 3 joule. So option here C, no, not C, B is the correct option. Okay, I hope we did some questions from this. Okay, we will check if I have a time, then we can finish this chapter laterwards. Okay, so I will end this meeting.